So now, when we have our sample, we need to identify the organic compounds we have in it. With inorganics, as we have seen before, it's relatively easy because atomic elemental spectroscopy gives you an unambiguous answer to a question, what elements you have. With organic compounds, we have literally millions of them, so the answer is not that straightforward. The simplest way is to use common spectroscopy. So let's look at caffeine and its UV spectrum. In UV area, caffeine has one peak. Actually, there is one more feature, the valley here. And we can use position of this peak for identification. In reality, there is some experimental uncertainty in position of this peak. You cannot measure it as infinite precision. So you can safely say that plus minus 1/2 or maybe even 1 nanometer will be your error, no matter how good instrument you have. Taking into account that we have from 200 to 400 nanometers for UV area and uncertainties around 2 nanometers from left to right, the probability of this peak location is around 1%, maybe 2%, because it can be any number in this interval. And if it width is 2%, 2 nanometers, 2 by 200, it's 1. Well, of course, the distribution of peaks of different compounds is not random number. So again, probability 100, 200 is reasonable. So if you have several compounds with different spectra, you can select your caffeine from that. Unfortunately, it's not very straightforward. For example, if you have theobromine, same as caffeine, just without methyl group, spectrum will be very similar, so you'll not be able to differentiate it. What can be done? We need more information. One peak is not enough. If we measure UV spectra in vapor, we have much more information because of vibrational peaks here that are overlap with our electronic peaks. You can see that even very simple tetrazine compound here gives you several dozens of peaks. Now, it's very difficult to bring organic compound in a gaseous phase. Usually we deal with solutions, and when we make solution of the same compound in hexane, instead of multiple peaks, we have series of much smaller number, 1, 2, 3, 4, 5, 6 peaks. Okay, 6 peak is not bad. The problem is when you are coming from hexane to water, you have only one of them left. So the spectra depend on conditions of measurement, and not always you can take the solvent that is suitable for identification. Anyway, of course, for identification purposes, 6 is much better than 1. For fluorescence, you can do the same trick. You can see that you have multiple peaks in UV spectrum, you will have multiple peaks in fluorescent spectrum, but sensitivity of fluorescence is literally thousands times better, so you can analyze much smaller quantities. The problem is few compound fluoresce. Now, if I have a single peak, can I make more information out of it? Yes, if I have a good instrument. I can take derivative of my spectral peak, and then I'll have more features to talk about. If I'll take the first derivative of Gaussian peak, I'll have such a shape. If I take second derivative, I will have negative peak instead of positive peaks, but I'll have two other peaks to the left, to the right of my main peak. That will give me information about width of my original peak. So I'll have 1, 2, 3 numbers now. If I'm taking fourth derivative, I'll have 1, 2, 3, 4, 5 points to talk about. So this can be helpful. Let's look at a real spectrum of protein compound. Shows one peak and some features barely visible on it. Very little information, but very low noise. So I can take first derivative, and now I have 1, 2, 3, 4 peaks and several valleys like this. So far more information. Taking second derivative brings me to 1, 2, 3, 4, 5, 6, 7, 8 peaks and 1, 2, 3, 4, 5, 6, 7, 8 valleys. So I can provide with 15 three-digit numbers. That's almost fingerprint. Accidental coincidence of 15 three-digit number is very small. This is very improbable event. The problem is that the resulting spectrum has high noise coming from the experiment, because you are taking difference by difference in any experimental problems will cause distortion of your spectrum. It's not easy to measure. Nevertheless, in this case, you literally have a fingerprint of your compound. Can we do it without taking derivatives? Answer is yes, but we need to go to infrared area of spectrum. In infrared spectrum, you have two areas. To the left, with smaller wavelengths, this is the area of functional groups, characteristic mainly to carbon-hydrogen vibrations of some sort. But starting with 8 micrometers, you're reaching fingerprint region where positions of the peaks depend mainly on carbon-carbon skeleton of your organic compounds. So if you have different isomer or slightly different structure, positions of peaks will be absolutely different and their intensities will be different. As a result, here you can see 1, 2, 3, 4, 5, 6, 7, 8 peaks, and isomeric compound has 1, 2, 3, 4, 5 absolutely different peaks here. So you can recognize which compound you deal with. In group frequency region, you can see that all your vibrations will be the same if the structure is similar. Of course, you can have some functional groups even in fingerprint areas, so you can find evidence of chlorine atom, for example, here. But otherwise, again, you have a large number of peaks that will help to identify your compound. As addition, you are using this area to prove that you have functional group like OH group here. Raman spectroscopy is complementary to infrared, so you can study the same fingerprint area with slightly different picture. You can see that in Raman spectrum, here and there, you have dozens of peaks of different intensity, and they can serve as a fingerprint of your compound, even if this compound is relatively simple. The problem with infrared and Raman is relatively low sensitivity. So when you have isolated enough of your compound and separated it from other, yes, you can do this identification. But if you have literally traces of your compound diluted in some solvent, in many cases, these methods are useless. If you can isolate solid precipitate of your unknown, the problem can be also solved with powder X-ray diffraction. This is theobromine, alkaloid of chocolate. You can see plenty of peaks here, and they are sufficiently good to identify the compound, even if there is a mixture of 2 or 3 of them. These spectra can be relatively easily simulated, even for compounds that are not known in powder. So you are using database, this software will make simulation, and as you can see, the whole picture is very similar. If you have enough compound, NMR can be helpful. So the same theobromine shows 2 methyl groups and one more hydrogen atom here, and one more hydrogen atom barely visible here. Not too much information. Many other compounds will have 2 methyl groups and 1 aromatic hydrogen. So in this particular case, this information is hardly reliable. Even more, the spectrum is contaminated with solvent peaks. This is from deuterated water, and this is from dimethyl sulfoxide. Alternative is mass spectroscopy. Now, mass spectroscopy is not spectroscopy proper. You are not measuring properties of molecule. You are measuring molecule itself, and the molecule dies in that process, crushing a detector. Nevertheless, we still say spectra because it depends of relative intensity from some parameter. In this case, our parameter is mass of our ion. Now, as you can see, we have 1, 2, 3, 4, 5, 6, 7, 8 strong peaks. Position of each of them we know to at least 3 significant digits. This, and of course intensity of these peaks, will give you information that will help you to identify the compound more or less unambiguously. There is a large number of databases The best of them at this moment is National Institute of Standard Technology database, NIST, that provides you with all the data. You can compare these two. They are not identical, but they are very similar. So from here you can see the locations of different peaks and compare with your measurements. The great advantage of this method is that you need literally trace amount of your compound to have your mass spec. This is a dramatic difference from any other spectroscopic procedure, and that makes mass spectroscopy method of choice for all toxicological research and all toxicological determinations. If you can do mass spec, you do it.